Good evening. So let's continue with this FIR filter designing. So the next characteristics is the designing methods. So in the designing methods, there are no specific rules. Okay. So what does this mean? This means that there are no simple direct formulas to determine the filter order, okay, which is the important criteria while designing a filter, because the order of the filter it will decide how will the transition phase or the amplitude response in the during the transition phase, that means from the pass band to the stop band or vice versa, it will behave. Okay, so this there are no direct formula to determine this filter order. Okay, and also we have seen the filter coefficients, they can also play an important role, because we have seen that output is given by your input signal convolution of the coefficient values, right? So when we try to determine these things, there are no direct formula for it. Okay, so what happens? So usually the common approaches that are being employed are the trial and error method. Okay, in such a method, we perform numerous computations and find out the best method that can work. Okay, and the second method is Kaiser method. So in this method, the properties of the window. So if you see in the designing of by trial and error method, so here we are using one windowing method. Okay, so this window it is being selected by trial and error method. Okay. On the other hand, when we talk about this Kaiser method, in the Kaiser method, also we will need a window, but the characteristics of the window it will be determined from the cutoff frequency, transition bandwidth, pass band ripple, and stop band attenuation. Okay. So, if you look into the explanation, so what it says is that a practical challenge in the designing of the FIR filter is like that. Now, unlike some engineering problems with straightforward equation, there isn't a single simple formula to calculate the exact filter parameters from a list of requirements. Instead, designers rely on the iterative or estimation based methods. Okay. So, what are the core challenges? As I already told you, this first we have to decide the specific goals. That means we need to know the specifications based on which we'll be designing the filter. So, what are these? These would be the cutoff frequency, transition band, pass band, ripple, stop band, ripple, and all these things. Okay, but the challenge is that these specifications are all interrelated, and you should have a formula which can help us in determining the filter order and the filter coefficients. But unfortunately, it is not the case, and there is no simple equation like filter order equals to function of the specification, and that is the most challenging part. Okay, so this is why the designers they have to use the sophisticated methods for designing the FIR filter. So the two common methods for designing the FIR filters include the designing by trial and error method, which is basically the window method. Okay, in the windowing method, we start with an ideal filter. Okay, then what happens is that we have discussed in the ideal filter, these are basically the analog filters. Okay, so they have infinitely long impulse response. Okay, so implementing this it is not possible, hence we have to apply a window. So what is a window? Window is nothing but a time domain function which will help us in truncating the number of the coefficients of the filters. Okay, so we have to apply the window. Then when we are trying to apply the window, we have to choose what type of window we want to use and what should be the length of the window. Okay, so there are several types of windows like rectangular window, fanning window, Hamming window, Blackman window, and so on. Okay, so the length of the window, it will determine the filter order. Okay, it will determine the filter order. Say for example, the length of the window is 11. That means the order of the filter is 11 minus 1, which is equals to 10. Okay, so if you are given with the length of the window, so the order can be found out by the formula length minus 1. On the other hand, if we are given with order of the filter, it will be given by this order is given by n minus 1, or length is equal to order plus 1. Okay. So once you have designed this, then you have to test and repeat the iterations by varying this filter order. That means the length of the windows and all these things, and the also you can vary the window type also, and you have to find out which one is giving you the better result. Okay, so hence it is called, it's an iterative process of refinement. Okay, now the second method, the Kaiser method, it is also a filter based method. However, by this method, we are reducing the guesswork. Okay, so herein what happens, we use empirical formulas. So these formulas are derived from the observation and experimentation rather than your theory. So from here, when we get the estimates, then we go for the calculation. Okay, so over here we have to give our input specifications. Okay, so we have to provide our desired specification to the Kaiser formulas. Okay, and once we have done that, we will be getting the estimated parameters, and these estimated parameters we get the filter order. Okay, in the previous case we had to vary the order or the length of the filter. Okay, in the second case, after we put in the values of the filter specifications, we get an estimation about the filter order. Okay, and then a special shape parameter for the Kaiser window, which is called the beta, it is also being calculated using the Kaiser formulas. Okay, so this beta, it helps us in controlling the trade-off between the transition width and the stop band. Okay, so what is the transition width? Transition width is basically the uh, what you call frequency band as we move from the pass band to the stop band. Okay, pass band to the stop band. So over there we are coming from pass band and we are entering into the stop band. So that bandwidth, it is called the transition width. Okay, so for usually for higher order filter, the transition width, it minimizes. Okay, so after we have got all these filter order and shape parameters and all these things, then we can go for the designing of the filters. Okay, so using this estimated order and beta, we can design a filter that is very close to or already meets our requirements. The Kaiser method essentially provides the blueprint that was missing in the pure trial and error approach. It's a much more efficient way to arrive at a satisfactory design without as much iteration. Okay. Then lastly, the filter characteristics versus complexity. So when we are having this in IR filter, when we are having the what do you call we are having the ability to use the properties of both poles and zeros. So usually we need a lower order filter. Okay, so in higher filters you will find, as we will design, as we will be going to design. So we, in common practices, we either go for the second order filter or the third order filter. Okay, we hardly go beyond the third order filter because most of the characteristics they are being met within the third order filter. Okay, so if you consider that thing, so what happens is that if you remember our transfer function hz, so what does that mean? This means, what does the order of the filter? How do you find out the order of the filter? Order of the filter is basically the number of highest number of poles or zeros. So whatever will be the highest number of the poles or the zeros, that is taken as the order of the filter. But we also know that for designing LTI systems or LTI filters, what we need? We need the number of the poles should be greater than equal to 0. So the number of poles in the case of higher filters, say it might be maximum 3. In the case of zeros, it would be again maximum 3 because it cannot go beyond that. Okay, so we are having only 3 zeros and 3 poles to deal with the computation part. On the other hand, when you try to design FIR filters, the order of the filters, they usually exceeds 50. Okay, and when we say it exceeds 50, we know that the shape of the FIR filters, the frequency response shape of the FIR filter, they are being governed by the zeros. But for each and every zero, we should have at least one pole at the center. So if it is a 50 order filter, so we will be having 50 numbers of zeros and 50 number of poles, and they will be there in the computation. Okay, they have to be incorporated into the computation, right? So if you see in the IR filter, what we are having computationally not very complex, but what is happening? The stability might be an issue. Okay, and also while we are having one number of filters, yesterday we decided, we have discussed, not decided, we have discussed that if we have to maintain the shape of something, we need greater number of poles and zeros, right? So in IR filters, in the pass band and the stop band, you will find the ripples are quite higher. Okay, so computational complexity will be smaller, but what is happening? You're you are deviating from the idealness. Okay, you are deviating from the idealness because you will be having more ripples in the pass band and the stop band, and the same thing goes, and the vice versa goes to the FIR filter. Since we are having larger number of this poles and the zeros, the computational complexity is very high, but what we get, the filter response, they are more towards the idealness. And another important thing we discussed is that we can design the amplitude response and the phase response separately. So we can design a linear phase response in the FIR filter. Okay, but that is not possible in the IR filter because the placement of the poles and the zeros, they are related over each other, and it becomes very difficult to what do you call it, to get both the things, amplitude response and the phase response, to an optimal level. So we have to come to a trade-off. Okay, so next, coming to the linear phase filter. So we already discussed, a linear phase filter refers to a type of the filter where the phase response is a linear function of the frequency. This ensures that all frequency components of the input signal are delayed by the same amount of time, and thus it preserves the shape of the waveform as it passes through the filter. So this characteristics is important in applications such as audio processing, communication systems, and image processing, where phase distortion can lead to undesirable effects. So key characteristics of linear phase filter: linear phase response that we have already seen, constant delay. Okay, that also we have seen. Then there would be no phase distortion, and FIR filters. Most FIR filters are designed to have linear phase by ensuring their impulse response is symmetric on antisymmetric, which guarantees this property. Okay, so based on this, we can classify the linear phase FIR filters. We can classify the linear phase FIR filters into four types: type 1, type 2, type 3, and type 4. Okay, so what happens is that type 1 filter, the length of the filter is odd, and the HN values, they are symmetric around the median value. Okay, अब चले जाओ, वो गर्म पानी बना रहे हैं. So similarly, in type 2, the arrangement of the HN values, they are again symmetric, and they have an odd length. Okay. Type 3, odd length, antisymmetric, and type 4, even length and antisymmetric. So you just remember only one, either length or the order, because if you try to remember both the things, you may get confused. So as per your understanding, you can remember any one, and from there you can find out if length is odd, then order should be even, and vice versa. Okay. So when we talk about this HN values, they should be symmetric. What does this mean? So this means across the line of symmetry, the values would be the same. Okay, the values would be the same. In type 1, if you see, the length is odd, so we'll be having a middle point. Okay, and across this middle point, we'll be having the values which are same on either side of the middle point. When we talk about this even length, in the even length, if you see, there are no middle point. So we have to draw an imaginary line, and across this imaginary line, if you see, the filter coefficient values, we are having same values. Okay, so here h0 equals to h of 4, h1 equals to h of 3, h2 equals to h of 2. Similarly, in type 2, h0 equals to h of 5, h1 equals to h of 4, h2 equals to h of 3. Okay, then coming to the antisymmetric, antisymmetric means the values will be negatively valued. Okay, so if you see across this line, if you see the values, they are opposite to each other. So h of 0 equals to minus of h of 4, okay, which is equal to nothing but minus of h of 0. Right? So h of 1 equals to minus of h of 3, h of 2, it is the central value, so its value would be the positive or negative, whatever. Similarly, for the type 4 filters. Now the thing is that if you look into this characteristic, so what is it? When we discuss about the type 1, using the type 1, we can design low pass filter, high pass filter, band pass filter, and band stop filter. Okay, if you see, all the types of filters can be designed. So what does this mean? This means that when we are having a length which is odd, okay, and then the impulse response, it is symmetric in nature, HN is symmetric in nature, then we will be able to design any kind of the filter. So this designing of the FIR filter by type 1 method, it is the most versatile method to design the FIR. When we try to design type 2, type 3, type 4 of filters, so what is happening over here? In type 2 filters, when you will be trying to design, so what will happen? It will happen that there would be a 0 at z equals to minus of 1. So when you will be having 0 at minus of 1, that means it is suppressing your highest frequency components. That means you will not be able to design high pass filter plus band stop filter. Because in band stop filter, what is happening? It is a combination of low pass filter and a high pass filter, and in between you are having a dead zone where there will be no signal component passing through. So because of that reason, this because you are having a 0 at z equals to minus 1, you will not be able to design high pass filter and band stop filter. Okay. Then when you come for the type 3 filter, see, there would be a 0 at plus minus 1. That means आपका low frequency component is also gone, high frequency component is also gone. So only option is where both these components are not included, and it is only possible to design the band pass filter. Okay. Then lastly, type 4 filter, 0 at z equals to 1. That means any filter which will be having low pass filter components or low frequency components, where we need this low frequency components, they cannot be designed. Say for example, we cannot design a low pass filter, and again we cannot design a band stop filter. However, we can go for high pass filter and the band pass filter. Okay. So in this short class, it is not possible to discuss all the things. So what we will be doing basically, we will only be discussing about the type 1 filter. Okay, designing of the type 1 filters. Okay. So Hz equals to this equation. So please design this or make this filter and make this what you call implement this filter or realize this filter in this way. Okay. So that we have already discussed. What I want to say you is that this is the direct form of realization, right? There is another type of realization which we call it as linear phase implementation. What we have seen in our previous lecture, in the previous one of this slide over here, Hn is symmetric in nature. Okay, Hn is symmetric in nature, right? Now, what does this mean? Two coefficients like the h0 and h4, they are same. h1 and h3, they will be having same. Okay, so in our class 5, 6 or 7, this thing, we have done something, some simplifications, linear algebra simplification. Say for example, I am given with two multiplications, say 3 into 4 plus say 12 into 4. Okay. In both the cases, we are having 4 common. So what we can do? 3 multiplied by 2, 3 plus 2 multiplied by 4. We can do in this way. So what we have done, instead of two multiplications, we have brought it down to one multiplication. So we have reduce the computation. Right? We have reduced the computation. Right? So similarly, in this linear phase implementation, we can apply that formula. Okay. So if you see, in this case, what we are having coefficient 1 and coefficient 1. This is h of 0. Here, this is h of 4. Then h of 1. Then h of 3. And this is h of 2. Now see, these two coefficients are same. These two coefficients are same. So we can bring the coefficients together. We can easily do it. Okay. So that is what it has been done in the next slide. So I will show it to you. So if you see, xz plus xz into z to the power minus 1, we have taken these adders and we have taken this multiplier outside. Then in the second one, this 2 is the common multiplier, we have taken it out. Similarly, the last one, it is remains in this form itself because it forms the middle value. Okay. So what we are doing now, if you see, it is very easy to understand. You just follow the thing. So we are having basically how many delays? One, two, three, four. What you do? Draw the delay in this format, in U format. One, two, three, and four. Okay. So in the U format, you make the delay. Okay. Join this. Then what is happening? XZ, it is not being delayed. You just bring it down. And this is getting added with which one? With four delays. So see, when you are putting it in this U form, it is here. So you just add these two values. And after adding, you have this multiplier. You multiply it with that. Then if you see x2 second delay and this one, they are forming, they are coming close by. Okay. So they are getting added up. Okay. Then after two delays, you are getting this one and everything now. And then you get the output. Are you getting my point? So 1 is multiplied by xz and xz delayed by 4 times. 1, 2, 3, 4, 4 times delays. It is getting added up. Then in this we are having 2. So from where it is coming? It is coming after x of z inverse. X of z inverse you have taken the output. And after z to the power minus 3. Z to the power minus 3 idhar hai. And just output of this one, you take it, add it up, and then you have multiplied with 2. And here what is happening? Z to the power minus 2. That means after 2 delays, you tap the value and you multiply with the 3. Okay. So this is called the linear phase structure implementation or linear phase implementation. So what is the advantage over there? The advantage is that here we were having 5 multipliers, but in the linear phase implementation, we were having only 3 multiplications. So that is decreasing our computation burden. Because in real term FIR filters, I discussed with you that the taps will be going into 50s, more than 50s, right? So, and in one system, you will not have only one filter, you will be having a series of filters. So the computational burden will be quite high, and hence this linear phase implementation, structure implementation is superior for hardware implementation. Okay, so this is what it has been explained. So in the next class, we will be going into the designing methods. We'll be getting into the numericals. So what I would suggest is that you take this example, implement it by the direct form realization method and by the linear phase implementation method. Okay, and after this one, you try to find out the impulse response. Any questions?